Sunlight is streaming in from outdoors through this tube. The big lens focuses an image of the sun on the slit. And over here, we have a spectroscope. The slit, a collimating lens which produces a parallel beam of light in this region, and a glass prism. Finally, the camera. We see numerous dark lines in the spectrum of sunlight. They were studied by Joseph Fraunhofer in the early 19th century. He used some of them as fixed reference marks to measure the values for the index of refraction of optical glass. In turn, these values enabled him to produce extremely fine achromatic lenses. Here we want to talk about a series of experiments by Fraunhofer in a different area of optics, in diffraction. In these experiments, he was led to discover the use of diffraction gratings as a tool for the spectroscopist. It's quite easy for me to modify this spectroscope for observations in diffraction. First of all, I remove the glass prism. The lens collimates the light from the source slit. The beam in here is parallel. The camera lens is focused for infinity. So, at present, an image of the source slit, irradiated by sunlight, is sharply focused on our film. To study diffraction patterns, all I need to do is place a diffracting object in the parallel beam. But before I do so, I would like to explain how Joseph Fraunhofer went about these experiments. Some of his apparatus and some of his diffraction gratings are preserved in the German Museum of Science and Technology in Munich, the city in Bavaria where Fraunhofer spent a large part of his life. This is the spectrometer he used for the study of diffraction. Fraunhofer did not have a collimating lens. Instead, he had the source slit very far away from the spectrometer, over 40 feet. The light arriving at the telescope from the slit was essentially parallel. With the eyepiece focused on the source slit, and with the slit image exactly on the intersection of the crosshairs in the eyepiece, the telescope's angular position was determined on this vernier protractor to within a few seconds of arc. Next, the diffracting object was placed on a table in front of the telescope. Finally, the telescope is turned through some angle, the angle of diffraction, at which some effect of interest occurs. This angle can be determined by again reading the lower vernier protractor. Now, we don't want to repeat Fraunhofer's precise measurements of angles here. We just want to describe to you what he did in a qualitative way and show you what he saw. He was led to realize the uses of gratings by looking at patterns from the single, the double, the triple slit, and so on. Let me begin by putting a single slit in here. Instead of the sharp image of the source slit, which we saw earlier, we now see a white fringe at the center. But light reaches our photographic film in a broad angular range on either side, in the form of spectra arranged symmetrically about the center white fringe. Fraunhofer studied this pattern, and he accounted for the appearance of each color in these spectra by the arguments of wave interference. Thus, the light appears purple at the positions indicated by the arrows because at these angles of diffraction, the single slit produces destructive interference for green spectral light. Blue and red predominate, producing the mixed color purple. This is the pattern created by two diffracting slits of exactly the same widths, placed parallel and close to each other in the same plane. The dark space between the slits is approximately as wide as each slit. Additional spectra have appeared, but there still is a central white fringe, although it is narrower. Symmetrically on each side, in orderly manner, one sees spectra, one following upon another. They are broader the further they lie from the center. We call this the first order spectrum. This the second, the third, the fourth order, and so on. Again, the colors are not the primary spectral colors into which a glass prism would disperse white light. This is because each monochromatic beam of fixed wavelength is spread into broad fringes by the two slits acting together, as you see in this picture, taken after we inserted a narrow-band red filter into the beam. Let's return to the two-slit pattern as it appears when the incident beam is white again. Take a look at one of the fringes, which appears purple, because the white light reaching it from the two slits interferes destructively for the primary green region of the spectrum. Only red and blue remain. They combine into purple. Other mixed colors occur at other positions, but in the center of the pattern, the two slits interfere constructively for all wavelengths. The central fringe is white. We'll now proceed by adding more slits one at a time, parallel to the two we are using here. Each will have the same width and will be placed at the same spacing as the others. Here you see the effect of adding a third slit. The central white fringe is narrower, and so are, in fact, the spectra of all the orders. An interesting new effect is the appearance of weak subsidiary spectra. Exactly one between the white center fringe and the first order on each side. In fact, there is one subsidiary spectrum between all successive main orders in the case of the triple slit pattern. A trace of the subsidiary spectrum between the main spectra of orders 1 and 2 is barely visible here. With 4 slits, each main order spectrum is narrowed even more, and the central white fringe, also narrower, begins to look more like a sharp image of the source slit. Now there are 2 subsidiary spectra between the main orders. Their number always equals the number of slits, less 2. The more slits one uses, the weaker will be these subsidiary spectra in intensity. In this 10-slit pattern, the subsidiary spectra are so weak that one can barely see them. There's another change in the character of these spectral patterns. It becomes more pronounced as more slits are added. The spectra of the inner orders are beginning to look more like primary spectra, like those which a glass prism would produce by dispersion. Look, for example, at the way the color red appears in the first order. Even in the second order, it appears more nearly like primary red, while in the third, one still sees purple. 20 slits. Note that the white central fringe is quite sharp and narrow. The main spectra of orders 1 and 2 are also quite narrow and neatly separated from each other. The spectra broaden and they overlap at larger order numbers. In this picture, we are viewing a multiple slit diffraction pattern in greater magnification. Moreover, for this exposure, we are using 300 slits. Notice how sharp and narrow the central white fringe has become. There's something else in this picture which is new and different. The new effect is not very obvious in the first order, but we do see, barely, some vertical dark lines within the diffraction spectra. They are more pronounced in the higher orders. These dark lines are Fraunhofer lines. Remember, our 300-slit system is being irradiated with sunlight. In other words, diffraction by a sufficiently large number of slits resolves spectral lines, just like a prism. Our series of experiments involving more and more slits is similar to one Fraunhofer performed around the year 1820. He probably didn't expect these dark lines to appear, but his powers of observation and of judgment made him concentrate on these lines. So, let's look at the spectrum again. It doesn't show as many dark lines as were produced by the prism spectroscope, which we used at the start of the film. Could this be a matter of bringing into play more and more slits, spaced more and more closely together? This is one of Fraunhofer's own multiple slits. By the way, one calls a system of multiple slits a diffraction grating. He made some of these out of wires, laid at precise spacings parallel to each other. He machined finely threaded screws. Then he cemented wires into each successive thread. His finest wire grating, which has unfortunately been lost, had almost 300 wires laid down at 320 per inch. He built a ruling engine and cut gratings on flat glass and on gold leaf cemented to glass like this one. Now, light of given wavelength lambda, normally incident on a grating, is diffracted into the nth order through an angle theta sub n according to this relation. Here d is the distance from slit to neighboring slit, center to center. Fraunhofer confirmed this relation experimentally with the dark lines as reference marks. Thus, if the spacing d and the angle theta sub n are known, a value for lambda can be calculated. For any one dark line in the grating spectrum of sunlight, Fraunhofer determined the diffraction angles with this spectrometer. To measure the grating spacings, he built a microscope. The grating was placed on the microscope stage, which can travel precisely measurable distances on a precision micrometer screw. Fraunhofer's finest grating was ruled on flat glass with a diamond point. It had a spacing d of 0.303311 centimeter. That means he ruled upon glass at the rate of 7,671 lines per inch. With it, he determined the wavelengths corresponding to several prominent Fraunhofer lines to 4 significant figures. We put together a grating spectrometer to take a look at the solar spectrum in high dispersion. The slit in the center is vertical. The lens on the right serves as a collimator. 30,000 vertical lines per inch are ruled onto the surface of this grating. It's a flat reflection grating 2 inches square. Such dense rulings weren't accomplished until the 20th century. By turning the grating, different colors of the spectrum of the sun will reach the camera. With such a fine grating, one can see many more dark lines than Fraunhofer could. Toward the end of the 19th century, the American Henry Rowland made gratings which had about 20,000 lines per inch. With these, Rowland determined the wavelengths of many thousands of Fraunhofer lines. These 2 dark lines in the yellow are only 6 angstrom units apart in wavelength. They belong together as a doublet spectral line and were traced to the element sodium about 30 years after Fraunhofer's death. Only then did the dark lines in the spectrum of the sun become understood as an absorption spectrum. But even so, Fraunhofer had made brilliant use of them in his lifetime. He had found a method for determining their wavelengths with precision. And that method works just as well for any other spectral line. With this film, we honor the founder of grating spectroscopy. So, at present, an image of the source slit, irradiated by sunlight, is sharply focused on our film. To study diffraction patterns, all I need to do is place a diffracting object in the parallel beam. But before I do so, I would like to explain how Joseph Fraunhofer went about these experiments. Some of his apparatus, experiments by Fraunhofer in a different area of optics, in diffraction. In these experiments, he was led to discover the use of diffraction gratings as a tool for the spectroscopist. It's quite easy for me to modify this spectroscope for observations in diffraction. First of all, I remove the glass prism. The lens collimates the light from the source slit. The beam in here is parallel. The camera lens is focused for infinity. We see numerous dark lines in the spectrum of sunlight. They were studied by Joseph Fraunhofer in the early 19th century. He used some of them as fixed reference marks to measure the values for the index of refraction of optical glass. In turn, these values enabled him to produce extremely fine achromatic lenses. Here we want to talk about a series of experiments. Sunlight is streaming in from outdoors through this tube. The big lens focuses an image of the sun on the slit. And over here, we have a spectroscope. The slit, a collimating lens which produces a parallel beam of light in this region, and a glass prism. Finally, the camera.